Hi, thanks for joining me today. I've got a cool geometry problem. We have 5 equally spaced points around a circle of radius 1, and I've connected one of those points to each of the other 4 with these pink lines here. What we want to know is what is the product of the lengths of these 4 lines. So what's P0 times P1 times P0 times P to P2 times P0 P3 times P0 P4. This problem has a really nice solution, so I really encourage you to have a go at this problem, but let's dive into a solution. Okay, so the trick to solving this problem is to put our circle onto an n-gon diagram. So the complex planes, we've got the real axis here, the imaginary axis here, and we're centering our circle right at the origin. And the great thing about this is then we can prescribe complex numbers to each of these points. So P0, well, that'll just be 1. P1 is going to be e to the 2 pi I over 5. This will be e to the 4 pi I over 5, and so on. In general, Pn is going to equal e to the 2 pi I n over 5. Okay, great. And so now what we want to do is consider what these distances are as complex numbers. Well, this first length here, P1 to P0, that's just going to be the magnitude of 1 minus e to the 2 pi I over 5. Similarly, this guy here is going to be the magnitude of 1 minus e to the 4 pi I over 5. This one, the magnitude of 1 minus e to the 6 pi I over 5, and this guy 1 minus e to the 8 pi I over 5. And so we're going to get a product of 4 terms there. I'm being a bit lazy here, not writing the middle terms. But okay, we're going to expand this out. So this is going to be the magnitude of 1 minus e to the 2 pi I over 5 times ... all the way up to 1 minus e to the 8 pi I over 5. Cool. Now, how on earth do we go about computing this nicely? Well, what we can do is consider this polynomial f of z. And f of z is just going to be z to the 5 minus 1. Now, what do we know about this? Well, firstly, each of these complex numbers here are roots of this equation, because if you plug in e to the 2 pi I n over 5 into this, you're going to get e to the 2 pi I minus 1, which is 1 minus 1, which is 0. So that means that each of these guys are roots of this, but also we know how to factorize it. So this is z minus 1 times z to the 4 plus z cubed plus z squared plus z plus 1. And if you don't believe me, you can just check by expanding that. Okay, so if I divide both sides by z minus 1, I'm going to get a function which I'm going to call g of z, and it's going to be z to the 4 plus z cubed plus z squared plus z plus 1, and this just equals f of z over z minus 1. Great. Now what I want to do is try and factorize g of z, so write it as z minus something times z minus something else, and so on. And to do that, we need to think about the roots of g of z. But conveniently, the roots of g of z are almost the same as the roots of f of z, except for z is 1. So we know that the roots of g of z are e to the 2 pi I over 5, e to the 4 pi I over 5, e to the 6 pi I over 5, and e to the 8 pi I over 5, like so. Those are the 4 roots of g, and so therefore we can factor g of z as z minus e to the 2 pi I over 5, and so on up to z minus e to the 8 pi I over 5, like so. So now we've got what g of z is. And so now, remember, we're trying to compute this thing here, which conveniently is just g of 1 when I plug in 1 into this, and then take the magnitude of it. So this guy here is just the magnitude of g of 1. But now, what is g of 1? Well, g is very nicely this thing here. And so g of 1 is just 1 plus 1 plus 1 plus 1 plus 1. And so this is just the magnitude of 5, which is 5. And that gives us our answer. So the product of these 4 lengths here is 5. So we've taken kind of a regular pentagon, a regular 5-sided shape, and computed these 5 lengths, and those 4 lengths, and they multiply to 5. I highly encourage you to see what happens if you look at a hexagon or a heptagon, or in general a regular n-sided polygon. You get a really nice result. So we'll finish off there for today. I hope you have enjoyed this video. It's a really cool result and gives you one quite useful application of complex numbers in geometry. Anyway, thanks so much for watching. I will catch you in the next one. If you have enjoyed this video, do give it a like. But apart from that, have a great day.